So I think everybody's here, so I thought maybe we could start. My name is Slava Gerovitch, and my email is on the board, which conveniently has my first name in it. Professor David Mindell, who is a principal investigator on this project, is speaking today on the National Public Radio Science Friday program, so I'm not sure if he'll be here. Sandy Brown, who is a research assistant and who's been in contact with all of you, is currently in New Zealand, and he couldn't make it back because of the recent tragic events. So I think these events kind of make us think that maybe we should appreciate every day of our lives that we have and try to do as much work as we can today. I will say a few words about the overall project for the sake of Jim Miller and Herb Thaler, who were not here at the first meeting. The project is called History of Recent Science and Technology on the Web, and its goal is to develop some tools that would enable veteran scientists and engineers to participate in writing the history of their particular disciplines or projects. So our role as historians here is just be your helpers to offer you some tools and to listen to you what you would like to have in terms of support and logistics that would allow you to contribute to writing history. There are different formats for using the web in this way. Some people prefer using web forums, or email lists, things like that. David Mindell has suggested that we would have these live meetings where people would exchange their memories and discuss some of the historical issues. Then we would have these meetings transcribed and put transcripts on the web where everybody could read them and comment on them. We also are planning to put, we're actually are already doing it, to put some archival documents up on the web where you could read it. Again, you could write comments on particular documents, on parts of it, which also be posted on the web, so people after that could come and see your comments and the original document and maybe write some other comments. So these are the kind of things that we're thinking about. If you would think that some other forms like a discussion list would be helpful, please let us know and we'll try that. I don't know if anybody of you took a look at the website, which is hRST.mit.edu. And it stands for History of Recent Science and Technology. Doesn't have any www. So this is the overall project, which includes 5 sub-projects, one of which is Apollo Guidance Computer, one is Molecular Evolution Theory, one is Bioinformatics, and a couple of others. In different fields, people try different approaches. We'll see what works in our case. So far, we had one meeting last month, and we already have a transcript of it, and as far as I know, it's been circulated somewhat, and people wrote some corrections. And we're planning to put it up on the web shortly, within the next couple of weeks, where you will all be able to see it and comment on it. I should mention that this website is a kind of working tool. So it has 2 layers on it. One is public, what everybody can see. And one is a working area where only members of our group can see. And so when you put your comment on the web, only members of our group would be able to see it at the moment. So because we would like to have it some kind of a place where we would be able to discuss our views freely and have some debate, and then we would decide to what extent we would open it up to the public. At the first meeting, we generally, I'm just saying it for the sake of Jim Miller and Herb Thaler, who were not there. We generally had an introduction when people talk a little bit about their role in the development of software for the Apollo Guidance Computer. And some of the general topics came up. What we would like generally to do is to focus on a few important issues in this project that would really made that project so salient and significant. Issues that, first of all, allowed that enormous enterprise to be accomplished successfully. So as Fred Martin, I think, put it last time, if we had to do this program today in the manner in which programs are done today, I don't think the program could have ever been done. I don't think that the amount of paper generated, the meetings, the views, the number of people involved, I don't think the program would have ever gotten off the ground. So it's a very interesting comment that suggests that the way that project was done back in the 60s was kind of unique, and we tried to recreate that uniqueness. And for that reason, your own reminiscences as participants are inviolable. That's something that documents cannot tell us. I would ask you to bring up as much as you can these elements of uniqueness, or something that distinguishes that particular project and you work on it from other things. If you could compare it particularly with other things that you encountered in other times, in other places or organizations, and to draw explicit comparisons that would help us to determine those distinguishing features, that would be particularly helpful. Another thing that we would like to do is to avoid writing kind of linear history, when basically what we often can see is just a line of decisions. First we did this, then that, then this, and that, and then it's success. There are always some points where different decisions could be made. There were debates when there were some roads not taken. Some places they had to go back and take another road and then go back. So we'd like to recreate that rather complex road map instead of just a sequence of solutions that were eventually found their way in the eventual product. So we'd like to have that sense of debate, of controversy. What exactly was the points of contention at different points of the project? Which design decisions or organizational decisions were particularly important and debated at that time, so that that history would be alive rather than a sequence of facts. A few things that came up in terms of topics that we discussed last time was the issue of the separation, the degree to which the automatic and manual systems must be combined in the guidance of the spacecraft. And as far as I can see in this discussion, mostly the issue of trust in the electronic equipment came up, and the astronauts didn't really trust it. So the automatic side had to be justified somehow. While in the Soviet program, curiously, and I should mention that I'm actually working on the Russian side on this story. In the Soviet program, mostly the issue was to what extent we can trust the humans. The opposite issue. So somehow the Soviets had a greater belief in automatic systems, in their reliability, and they thought that humans was the weakest link. I'd like to, if kind of frame that issue a little bit around this this question. Maybe these issues came up in your project as well, but you simply didn't mention it. So that would be interesting. Another thing is man-machine interface. To what extent the astronauts had an input into the way they wanted to interact with the computer. To what extent computer designers had their say. The role of warning systems, to what extent computer was allowed to let the astronaut know that something that astronaut is doing is not really right. The issue of memory constraints and speed constraints that really put a limit on these kind of backup and warning systems. Also, a series of implementation meetings was mentioned, and the issue of disciplining the software program, introducing all sorts of measures that kind of streamlined that process and made it manageable from the NASA point of view. And I would like to Maybe if you could say a few words about the way that was done, how it was accepted, what consequences did it have, and a little bit more detail on that. And lastly, the question of openness of the whole project. Again, there is a startling contrast with the Soviet program, which, as you know, was all classified and run under the military umbrella, while the Apollo project was open. And some of the participants in the last meeting stressed that it had a very important role. And I really want to push you a little bit on that and see whether this openness actually maybe posed some problems for you in terms of interacting with military people. Maybe military people didn't want to tell you something because they knew that your project was open, or I'm just speculating about that. Maybe it was no problem at all. So maybe you could say a few words about that. Today's meeting, I would suggest to start by asking Jim Miller and Thaler, who were not here the first time, to
Alex.
Alex Kosmala, I'm sorry, to introduce themselves and to talk a little bit about your role in the Apollo Guidance computer story, and then we would go around the table and have people talk more about the issues. Start with Alex.
Okay. I think I joined the lab in '63.
For the second. For the second time.
For the second time. Dan was one who winkled me out of England to come over at the start of the Apollo program. I came as a physics graduate. I knew nothing about computers, analog or digital. I knew nothing about programming.
I knew that.
And one of my observations, actually, it has to do with that, because one of the successes here, I mean, I know when Margaret joined, she didn't know anything about inertial navigation systems. I hope I'm not putting words in your mouth. And yet, we grew this knowledge to the extent that we needed to understand it, to control it, the right programs that controlled it. To me, it was always amazing that so few people, relatively inexperienced in the subject that we were dealing, they were just smart people, managed to acquire enough information from a vast array of resources around us in the lab to not be blocked by a wall of ignorance. I can't move because I don't know. You wouldn't have found out. You talked to people. And there weren't very many people that you needed to do that with. To me, one of the strengths of that program was the few people that were working. And we always came to the conclusion, Dan and I talked about this in the early days, that the optimum size of a software group producing complicated software like this was about 5 or 6. Because during some of the stressful period where we were really churning stuff out, there were little knots of 5 or 6 people that really put the foundations to this. One of my roles when I began to feel my way around, that I can remember, and my memory really starting to come apart at the edges, was to integrate some of these areas. There was a launch area, there was a re-entry area under Dan, there was a powered flight area, who were investigating some of the technical problems in these various areas. I had to stick these together in order to achieve our first guided flight, which I still have pictures and stuff of, from which we knew as Apollo 202, is to manufacture the glue and just make stuff up that integrated the astronauts' actions, the powered flight equations, tracked the launch, which we didn't control. So when the time we took over, we knew where we were and how fast we were going and so forth. Then we took over. The mid-course stuff, which was a whole nother ball game, which I knew absolutely nothing of, and even at the end of the program, I really didn't understand it very well. So my role was to knit some of these pieces together, and my memory is dim, but it was a heck of a lot of hard work, long hours. Stuff didn't work. Stuff we made up as we went along didn't work. But in the end, it all did work. If I remember rightly, that first flight landed remarkably close to its objective in the Pacific.
Being late for lunch because I wouldn't let you go and you were dying of hunger. Yeah. You remember a few of those, right?
Anyway, I can ramble on, but I think to me the amazing thing about this, looking back, was the quality of the people, the fewness of the people, the immense support that you got from all the resources that were arrayed around you. The openness, I guess, is what you were referring to before. We ourselves, at least that's what I felt, were the only blocks, you know, because of ignorance. But we overcame that as we went along and we made it work. I'll just shut up at that point. I'd like to hear what some of the other people...
You'll get another chance.
All right. Jim?
Not sure exactly how much of what to cover, but let me cover some things briefly about how I got there and what I did. I evaded the draft during the Korean War by going off to graduate school and staying in college, got a master's degree in electrical engineering, and that was as long as I could postpone being in the service, and I entered the service in 1956, Air Force, and was assigned to a place called Cape Canaveral or something. I never heard of it. And John Daly, who read the news on the TV, hadn't heard of it either, and that's how he pronounced it. But within a week or two of being there, I was out at the Cape and watched the Redstone launched at night, and I was completely hooked into the idea of rocketry and guiding the things, and stayed in the service a couple of years, and came up to MIT to get a doctorate in a program Dr. Draper ran called instrumentation, which was a combination of academic disciplines, multi-departmental. I started writing code for computers in '57 or something. We had a digital computer down there, and eventually I got into programming it for whatever reason, and writing my doctoral thesis, I got into both celestial mechanics because I wrote on the guidance of a 1 pound thrust rocket vehicle from Earth orbit to lunar orbit, 1,000 pound vehicle with a 1 pound engine, if I recall. Takes a long time to build up the energy you need to get out to the moon. But in the process, I learned a lot about celestial mechanics and trajectories and about writing code for computers. And I really have to say that the computer part of it appealed to me more than any of the other parts, although I liked celestial mechanics. But when I finished my work, Dr. Draper had, through his incredible influence, landed a sole source contract at the laboratory, instrumentation lab, where I was sort of based, to do the Apollo guidance system in late '61. And with Bob Stern, Dick Batten, and Hal Lanning, we were a group of what I think was called advanced guidance or something to work the Apollo problem. There were other people in the Polaris side that were busy as well, but we started without my really having any contact with those folks. I worked on trajectories and trying to figure out abort trajectories and so forth. But pretty soon, maybe that was later, but Hal Lanning had written an executive and an interpreter for a computer which was being proposed to be the onboard computer for Apollo, which was a computer that had originally been intended to fly to Mars and take one photograph and come back and drop it somewhere where it could be retrieved. It never happened, but that computer, which was a 15-bit computer of all things with 3 bits for opcode and 12 bits for address, was very nicely designed. It had 8 opcodes and 4K of memory, of which I think 500 words were erasable and the rest was fixed memory. These folks know more about that than I do, but Hal had written this executive that dispatched tasks on a priority basis, and an interpreter, which was something I'd never even thought of or heard of. Hal was probably not the first to do that, but a real pioneer in a lot of ways. But he had written this code, and I started reading it and trying to make it better, which was difficult. But it occurred to me that one of the things that we're going to need is something that simulated that computer, because we didn't have a computer to run, and if we had, we wouldn't have been designed for debugging and so forth. So I got eventually into the game of writing a computer simulator for the Apollo, for what we call then the Mars computer. And that developed over time, and I sort of skip around a lot, but over time into a full simulation of the spacecraft, the guidance computer, all of the hardware that interacted directly with the computer or that controlled the spacecraft, and even with the crew, including where the fixed stars were and all the sextant operations and so forth. And ended up in the library developing the star catalog, which as far as I know was the one that went to the moon. Well, I don't really know, I lost track of it. But they don't change very fast, so it's probably stayed the same. And the group developed into, I don't know, half a dozen people or so on different aspects of writing the simulation. And we were racing to get it ready in time for Alex's 202 software. And I say Alex is because he was in charge of it and bore the brunt of all the stress. Other folks just took life easy and
like Margaret.
Margaret and Dan and so forth. But trying to keep up with their needs to do the simulation. We had at that time moved from the 650, the powerhouse of the instrumentation lab, up to a Honeywell machine, which was designed to do insurance programming, I think. It had lots of tape drives, and a fun machine, but wasn't quite fast enough, so we eventually got a faster one, and then we moved on to IBM machines.
Is that the one with queasy ode on it?
Queasy ode.
I remember one day we had two 360-75s, just about the world's fastest commercially available machines, other than maybe some of the Cray, Seymour Cray's machines. And we had fixed it up so each one had two big 2314 arrays. 2314 was a big disk drive, which about the footprint of this table, it had 8 multi-platter disks in it, 9 actually, because one would fail or something. Well, I guess it was for loading up another one. Well, the other ones were in use. And as I recall, we had 2 of those connected to each machine, and because of cable restrictions and the distance of the machines, we had a 5th one that was sort of halfway between the 2 machines with a cable running from each, so we had a shared disk. And I remember standing there thinking, we have a gigabyte of storage on this machine, almost, between these machines. And I thought that was, it was at the time absolutely mind-boggling. Not nearly as mind-boggling as what's happened since then.
You should point out a megabyte on the 75 cost about $1 million of
Well,
regular storage. The
machine that I ordered, the 75 that I initially ordered, had half a megabyte of memory, and little did I know, and it fed 4 2311s because the 2314s weren't available. I've forgotten how small the 2311s were.
28 megabytes.
They were small,
Yeah.
and the operating system used up, I think, all of the disk space and all of the memory, leaving no space for anything else. But memory was so expensive, we had to buy, we went up to a whole megabyte. I remember I was living in the Netherlands, bought a megabyte of memory for my AT that I had bought, and rode home from the electronics store with a megabyte of memory in my pocket on my bicycle. And I thought, gee, things have really progressed. Now my 60 gigabyte disk that I have on my machine at home fits in my shirt pocket. Just can't believe what's happened. And it is very difficult for me, having even been there, and I think for people who weren't there, almost impossible, to imagine the difficulties that people dealing with a machine, with a 15-bit word, and lots of restrictions on expanding it, even though the technology was available, the reliability requirements prevented much happening that would take advantage of what could have been done. Trying to squeeze enough software in there to fly to the moon and back into what became, I think, 36K words of fixed memory and a 1K of erasable memory. 2K, yeah, and 1K accessible, and right. And squeezing that out of a 3-bit opcode and a 12-bit address took some funny shenanigans, which caused a lot of debugging activity. But I don't think anybody can imagine that the kinds of problems that were faced trying to squeeze a huge amount of software into that tiny, tiny machine, which really was small. After getting the simulation group going, and there are lots of war stories about that, probably of little interest to most and known by the folks here, I foolishly accepted the responsibility of becoming the leader of the mission program for the first lunar module. This was after the Apollo fire, long hiatus of flights, during which time everybody moved to the Block 2 stuff. And I remember the long time it seemed that Alex was sweating and working on the 202 software. The 204 software, it never flew. It was going to fly in that, which the 3 astronauts died on the pad. But I went to Alex, and I don't know if Alex remembers this, but I remember it, and I told a lot of people. I said, Alex, I didn't know anything about the mission software. I've been doing the simulation and trajectories, and I know all that stuff cold, but I don't know anything about the mission program. What do I do? What did you do? He says, well, anytime somebody comes to you and asks you what they should do, make something up. And I said, you're kidding. He said, absolutely not. He said, if they come to ask you, they don't know, and they know better than anybody else, so if they don't know, and you don't know, you got to make something up. Well, he was exactly right. It worked. You just had to not get stuck on something. You just had to take a path, and not all of the things that either of us made up probably, but certainly in my case, it worked. But if it didn't work, you found out about it, and then somebody would come back and say, this didn't work, what should I do? And you make up something else different. And that usually worked, because then you knew. It was a seat of the pants a lot of the way. And that's probably a good place for me to shut up for now.
After about 11:15.
Well, I got involved in the Apollo project by way of sort of a back door. I was working for Raytheon and attached to the instrumentation lab on the Polaris project as a resident. And shortly after that petered out a little bit, I became reattached as a resident on the Apollo program in the computer group. And when I, just putting things in context, I was all of 3 years out of school. So not what you'd call really tremendously experienced in computer design, but got into the computer group and was doing work with Ramon and Dr. Hopkins, Dave Shansky to go ahead with the Mars computer. And then shortly after arriving, the concept of the integrated circuit arose. And I remember a meeting in Eldon Hall's office where we all gathered around and tried to determine which direction the group ought to go as far as implementing either with the Mars circuit technology, the core transistor logic, or the integrated circuit approach, and all of the issues that was going to raise. And the decision was made to go ahead with the integrated circuit approach. Of course, none of us knew what an integrated circuit was at that time. But I ended up with the responsibility of re-implementing the Mars design in the integrated circuit world. And carried that through. It's a very interesting computer design, many levels of interrupt. I remember words like pink, mink, shink, and shank for essentially instantaneous reaction to requests from resolvers and synchros and communication links and things like that, and a multi-structured level of interrupts and software levels of hierarchy. I also remember a fateful day in 1963, sitting in the Apollo Computer Lab, which was a big room and then a little room behind it. I was in the little room behind it with the first brass board Apollo computer prototype. I was debugging it when the word came that Kennedy was shot. That was kind of a real seminal moment. I think everybody became particularly re-energized in making this project work. And that was my role. I did a little bit of programming when the design was finished to some orbital calculations. But my role was primarily in the design of the hardware.
I'd like to add something to what Herb did, which was a quote, which I think applies to the business of you couldn't do this project today. At the time, the Apollo computer first became kind of available. There was an internal need to have something that could show that it worked, not that it did the job, that this computer was alive. And Herb programmed a little game which would be completely primitive by today's standards, but it was a little version of Pong in which the ball bounced all over the place. And it was after doing that, and then all the work that came after that, I heard Herb one day say, you can do so much with 4K and so little with 40. You know, you can do so much with 5 people and so little with 400 people all trying to do the same job, which I think is part of the thing. And what I think in terms of why the project was done, I think the genius was in the partitioning of the project. That, this had several geniuses. One is having a clear goal, the other having an institution that was already was talented. You can't do that. You're not going to go anywhere. But then the fact that the job was broken up so that the people go work and as to what they did, and didn't have to constantly cross-check everything at every second. There was plenty of that to be done. But I think that that's probably one of the signal characteristics of that project. I've been in many projects since then, and I mean everybody here has too, and I think that those projects that fail almost always had enormous bureaucracies of cross-checking that just didn't seem, in other words, the partitioning was wrong.
Do you think that right partitioning was it achieved by intuition, or did that idea come from somewhere? Well,
generally there's got to be a combination of political and technical architecting done. I don't know if it's any one person, but I think the lab had, first of all, the lab was divided by stovepipes. So there was the gyro group, the inertial platform group, then there were the signal conditionings, and then the optics group, and then the computer group, which was kind of a foreign object in the lab, as I recall, for many years. So that partitioning by discipline already existed. But even within that, I think once the job was done, that there was going to be a midterm guidance and a booster guidance and a reentry, and there's going to be an abort. And all these things were partitioned. It's probably Davy Hoag was the person who just thought that this is the way the world should be. So I think that it requires a architecting visionary on that. So.
Of course, spaceflight consists of a lot of periods of thrust and activity followed by long periods of just tracking where you are flying to. And so some of the partitioning just came from the separation by periods of quite inactive flight.
Do you want us to, are you through over there? Should we all start?
Sure. Now it's all yours.
Well, I think two things. One, the overall speed. I think you got to look there. It was a totally different era. It sort of had followed not that long after World War II, when it still had the spirit of whatever you got to do it quick and done, because there's a pressure. And the aerospace industry, for instance, started with nothing when the 41, and by 45 they had built 300,000 airplanes and bombers and transports. So they had an industry that really tooled up and moved fast. And after Sputnik, we were in another mode of moving that way. Some of us had worked with Davy Hoag on the Polaris, and we worked on the guidance and so forth. But those guys, Admiral Rayburn and his special projects, they said go. In 18 months, they had a submarine built and ready to take a missile by shortcut. I mean, imagine sitting down now and saying somebody go and saying, building a submarine and having it out there in 18 months. You couldn't do the paperwork in 18 months. But those guys really, really moved. I never quite understood. Well, they took a submarine that existed and split it in two and redid, took all sorts of tricks to do it. But those of us who worked on that also saw that whatever you did, it was going to move very, very rapidly. And we had Davy Hoag to lead us, who's really a genius as far as I'm concerned. A lot of us think he's the mentor for engineering, showed us what engineering really was. Then when we moved to Apollo, which Davy said last time was August 8th, 1961 was in Washington when they awarded it. And some of us were there then, so we were there from even the start. But it started, as Jim said, then they started put together teams. There was a little before, but not much, and built it in late 61. But you got to have there's really two distinct phases with different objectives and organization. First is the engineering phase that lasted, 2 to 4 or 5 years, depending on what part. And that's when you had powered flight, rendezvous. I was in the reentry, something else, LEM later, but I don't know that it started that way. And you guys were doing the simulator. Who else? There was about 5 or 6 groups, but it was definitely engineering organized to different parts of it. And Dick Batten was the guy that ran all of it, but we were all involved.
He didn't really run it.
He didn't really run it. He just nodded and let you do. He presided.
And he was a real hands-off manager,
right.
Just a guru in his corner office.
Very smart in his corner and smoked his pipe and nodded.
Everybody thought he was just writing a book, but by God, he knew exactly what was going on. And he didn't interfere. And to me, that is one of the secrets of success. Again, as I said before, it was the fewness of the people that allowed this massive project to be shoehorned into this teeny box and work.
Engineering groups was quite small, as things said. We had 3 or 4 in the reentry, and each of these others didn't have a lot. And you had a free hand. NASA was very busy with a lot of other, they had a lot of other things cooking, so we had a lot of ability. We went to these panel meetings every month or two. In my case, it was Aaron Cohen, and a lot of other NASA that you informed them what you were doing and waited for critical comments, but you weren't ridden.
Yeah, I had a single point of contact at NASA. Tom Gibson, remember him?
Right.
The cigar chomping guy.
We did
He oversaw our work, but he didn't interfere.
Right.
We told him there were not hordes of bureaucrats who caused you to fill in forms and make present-day briefings and that kind of crap. We didn't have that at all. But you kept Tom happy. He kept them off your back, and you went on with the engineering.
Then we awoke several years later realizing we had a big programming problem. So we switched from the engineering, develop equations, make simulations, study, develop guidance equations. We shifted to a different mode. We had to program this AGC. And now we needed a new organization, different people leading it. The organization changed entirely. And now it was more mission-oriented, where you integrated all the needs into, like he started the 202 one, and different people took over other ones and integrated the efforts of these different groups and really had to program it, because in most cases the engineers did a so-so programming job and it had to be redone and put into a form that would be all consistent for a particular flight. And you know, you found stupid errors from engineers here and there, like somebody for pi using 22/7. We kept getting errors and couldn't figure out, and then this guy, I mean, he was in the old school.
Good enough for a slide.
Good enough for a slide.
And there were subtle errors that even got to the flight. You think Earth rate is a well-known constant, hasn't changed very much. Earth rate is Earth rate, but for us novices, although we know more at the time, the Earth rotates once in 24 hours. And that's what the guy used on his calculation, but that isn't right. The Earth does not rotate once in 24 hours. 24 hours is when it gets back to the sun again, but if you're doing the Earth's rotation rate, it actually rotates in about 23 hours and 56 minutes, as I recall. And if you use the difference, your longitude's going to be way off, which it was on I can't remember what early flight there was. So things did get through, but the programming effort was directed differently and organized differently, and these guys really, Margaret, Alex, Fred,
Lots of
all
others
really
weren't, yeah.
took over and in a very good way to lead all of those. Then we had a break into LEM versus command module. LEM engineering took a lot longer because Grumman was longer. They didn't know. Some of us thought we were done, and they were just almost getting started, Alan Klump. And then the autopilots came along, which required some more engineering. Anyway,
For a long time, there was a myth that was absolutely nothing more than a myth, that each mission program was a slight enhancement of the one that went before, so that all you had to do for the next one was the enhancement. The myth part was that you had to start all over again because everything was different. Somehow the hardware was different, or the mission was different, or there were very few things that...
I think I'm the only one that we flew exactly the same thing twice. I don't think there's any other. Maybe you got 501 and 502 were identical because they were unmanned, there was nothing, and I think it was absolutely the same thing. But I don't think we did any others that way.
But the trouble is, a lot of us were fooled into believing the myth somehow, even though after we knew it really wasn't working that way, and thought with these small groups of people we could handle it. And
Yeah.
I remember these talks in which we said, we got to do this with either about 5 people, maybe 6, or we got to do it with 150. The number we've got, which is about 30 or 40, is absolutely going to kill us if we keep on. We have to do either one way or the other. I think happily we went to the 150, although it wasn't fun at the time.
No, it was very difficult.
A whole new culture.
Especially when you had, what's his name from IBM's, Brooks' law, that adding more people to a job that's in trouble makes it later and things like that.
We couldn't figure out why anybody else needed to know what was in the guidance computer besides us. What does NASA need to know for? Why do we have to publish all these documents? But we, of course, did have to publish all that stuff. Speaking of the point that Fred apparently raised in the prior meeting and that Dan touched on, I remember I mentioned Hal Lanning, who had written the executive for the Mars computer, and who stayed involved for a while, but decided he didn't like the big money and the big pressure, got off. But one day there was a meeting sort of late in the Apollo project in which it was a 2-day meeting at the laboratory of about 30 people to decide whether the executive program for the shuttle computer should be interrupt-driven or schedule-driven. And I'm not sure it came to a conclusion after 60-person days. But Hal said to me, these people have just spent more time, more man days in that meeting than it took me to conceive of and write and debug the executive for the Apollo computer. I mean, things just had changed by orders of magnitude. And it was clear to me it wasn't going to be fun anymore to work on that sort of stuff, and so I didn't.
I'm very familiar with this particular issue, and I'll get into it a little bit later. It is the tale almost of a long story of that I would categorize as almost a religious war between the synchronous executive folks and the intra-priority-driven folks, and it mushroomed in the shuttle program, and it had its roots in Apollo, and perhaps I'll get into that in a little bit later.
You asked about trust in automatic systems. I remember just a short anecdote. We were visited at the laboratory one day, and I don't remember when, but fairly early on, by John Glenn and Al Shepard, and I think there was a third astronaut. I don't remember who. And it was at the time when reporters were still chasing around after the 7 astronauts, and it was a big thing when the astronauts were coming. And the laboratory was sort of showing those folks what we were doing. And one of the things that at the time we kind of had the arrogance to believe we should do was to make sure that nothing could be done by mistake by the crew that would endanger them. So there were a lot of tests that said, if the delta V is in the wrong direction or this or that, I can't remember what all the conditions were. There were lots of conditions. Then they couldn't execute the proceed order to go ahead because something was, the software thought something was wrong. And Shepard, with his marvelous way about words, I remember 2 things he said there. But this one, he said, you guys think you know more about what is going to face us during flight than we will know during the flight. He says, you're wrong. He said, take all of those inhibitions out. He said, if we want to kill ourselves, let us. It could involve saving ourselves. And of course he was right, and I think everybody sort of woke up to that. It made the software a lot easier too, so you didn't have to worry about all those checks. But he was adamant about that.
It did let him start the pre-launch program on the way back from the moon.
Well, they weren't capable of perfection, but they were pretty well trained, and they certainly were motivated.
They were very well trained, I will say that, but they also got very tired.
Yeah.
I had the reentry, which is at the end of 5 days out there, and they swore through all the early years that they were going to fly it manually. And as far as I know, none of them ever touched the manual stick. I mean, they were so beat, and then all of a sudden you hit 7 Gs. I'm not sure they could even see what was going on by then, because, I mean, they didn't get any sleep out there for all that time. They really didn't. I'm surprised they were doing as well as they did after all that time.
Yeah, I think we had a different opinion of this subject matter than the astronauts did, or at least the software group did at the time this took place, the pre-launch. And we talked about that the last time when we selected pre-launch during flight. So I think there's sort of a in-between, sort of, you don't want to overdo it, but you also want to make the crucial areas where you can't have a catastrophe. So.
Shepard in that meeting was responsible, I think, for the demise of another thought that we had, which was that computer not being perfectly reliable, it was going to be possible to do in-flight repairs. And so there are a lot of thoughts about diagnosing what had gone wrong and changing modules and so forth. I don't know how far along that got, but Shepard's comment to that was, yeah, and we should all train to be brain surgeons so we can operate on each other. And I think that was about the end of the in-flight repair.
I think there were two eras here that people are talking about that somewhat different. There was the sort of small group, seat of the pants effort that was unfettered and unhindered for the most part by NASA and devoid pretty much of real bureaucracy. And I think that, as Dan pointed out, you had a lot of the fundamental engineering work was done during that period, and it was very fortunate that we were able to do it unfettered, because I think that a lot of the fundamental issues on how to get to the moon, let's say, were solved in this period of isolation, or almost isolation, and small groups. And these various flights that have been talked about, I think the term, when Alex was talking, the term system mother came into my head.
Rope mother.
Rope mother.
Yes.
And this was a person who was, the responsibility was focused upon this person for a particular flight, even though it was a relatively small group. But I think this era was, I would say, this is the pre-Bill Tyndall era. Mm-hmm. And I think that somewhere along the line, someone did some, let's say, back-of-the-envelope calculations about how many lines of code we have to do, how many lines of code per person month, and things like that, and came up with a number of people that were just completely different than what the lab had in doing this work. So instead of having 30 people, we needed 200 people, or something like that. And not only that, but we needed all this documentation, and we needed all these review meetings, and we needed all NASA supervision, and we needed a lot of stuff. And at that point, there was a LEM that was being split off, and we sort of became, quote unquote, professionalized, in the sense that I remember one day, and I can remember the day very, very clearly, that there was an evening meeting about 7:30 in the evening, and with Ralph Reagan running the meeting, and the lab has been under a lot of pressure in previous weeks with respect to NASA coming down and questioning their organization, and questioning their documentation, and questioning their testing, and questioning everything. And I was told that evening that we're going to have different organization, and we're going to have something called project managers. And we didn't have any project managers. We didn't have that title anyway, even though you might think of a rope mother being a project manager. And that's when I was appointed the project manager of CSM software, and another individual, George Cherry, was appointed the project manager of LEM software. And these groups now were fairly large, and NASA wanted to see formal schedules and you know, time to complete this module and time to complete that module, and reporting on a monthly or so, or what, I can't even remember the schedule, what it was, but things started to build up in reviews, and in paperwork, and in monitoring, and so on. And I would say that became a different era of doing work at the lab, and much less fun for a lot of people.
Can you put a date on that switch?
It was after Gemini that NASA descended on us, but I don't know quite when the date was.
I would say, I'm guessing, and I'm doing it on my own time schedule. I would say it's either in the fall of 1960. I think it's the fall of 1966, or I don't think it's into 67, but
by 67 you were in place.
I think it was the fall of 1966.
And what do you think actually prompted that change in NASA's attitude? Was it the concern of one particular failure?
Well, I think that's a very good question, and I have an opinion, but it's just a completely personal view. The people at MIT were very smart, very talented, we certainly produced a lot. But we were also, I think, sort of arrogant from the outside. And I think that arrogance started to irritate people who were tired of hearing that MI2 knew best and knew better, and you don't even know what you want, we know what you want, and so on. And I think that that was part of why there was an effort to almost sort of rein in MIT, or to get them on this program, not their own program, and that NASA's the boss, not MIT. And I think there was a little bit of that. Plus, there may have been some perfectly honest professionals at NASA who had experience with large programs and just felt that this was not going to get there in the manner in which it had been going so far.
So you don't recall any particular conflict that may have prompted?
Well, not.
Well, those operations guys that you see down in all those rooms in Houston were doing first Mercury and Gemini and zillions of them, and flight controllers, and all of a sudden they said, now what are we going to do for Apollo? And they had nothing in the way of documents, procedures, all of it was really
Let me tell you what they
scanty.
created down there after a while. I can remember this. They had at NASA at Houston on the 7th floor, in building 1, I think, had this beautiful conference room, really beautiful conference room. And that's where they held a lot of their big conferences. And they built a wall on this conference room of sliding, sort of translucent boards that were like this blackboard, whiteboard, and they were white, and they went deep, like 6 deep, so that you could push one, and there was one behind it, and push another one, and you had a big, long, it was about the size of this wall, and you could move things from one side to the other, and so on. And on this wall, they created a schedule, like today, like we call it a Gantt chart, and they had somebody who was taking care of this, some contractor who would come up every day with his blue tape or red tape or yellow tape and mark where the schedules were and all these things and what was going on. And they could roll this board back from that board and so on. And this was being eventually kept daily by this contractor. And it was magnificent to see it. That's how much they got into the schedules and the sort of the project management of the program.
Yeah, and MIT was woefully unprepared for all this tons of stuff and support and so forth. So they had to reorganize all together, and it would have been, I don't know how it would have worked. There were a few people like Fred who really did a great job of dealing with them and trying to shake the rest of us up to put on some reasonable form for it. Plus, there was Bill Tyndall, that you have Tyndallgrams that we dealt with, who was up here a lot trying to work the problem, as they would have said in those days. And say what you may, he did a great job in trying to match the...
So were you kind of seriously adapting these techniques in your own group, or were you just kind of shielding that group from NASA?
Well,
allowing, kind of old practices in the group still
I would
go
say,
on?
there was a certain amount of shielding, but I would have to say personally, I was trying as a project manager to adopt project management methods. And I was trying to keep track of schedules, and I was trying to encourage people to document things and put documentation in listings and so on and so on. So in that sense, I was almost one of the enemy, if you want to put it that way, because there were a lot of people, and I'm sure looking back at it, people would still have those feelings that this was just, all this nonsense was just getting in the way of getting this job done. Well, NASA just didn't view it that way. I mean, that
right.
was part of the job. You had to work to schedules. You had to work to You had to have reasons why you couldn't meet a schedule. You couldn't just say, well, you know, I promised this in 2 weeks and I couldn't get it. You know, I was.
But I think one thing that helped, it was a matrix management setup.
It definitely was.
And so Fred and George at that time were project managers, but then there were the functional managers. So while they were worried about the schedules of each mission, then the functional people were worried about, hey, is this stuff working? You know, the stuff we're supposed to be delivering, the actual, maybe the man-machine interface part. I mean, this was a whole separate division. So the functional people and the project managers I thought they worked together very well.
Well, there was a certain amount of tension. There's always tension in a matrix organization.
But
Fred did a great job, because he
Yeah.
came to us and wasn't as high-handed as some people at NASA, and pounding on the table, give me this or else.
No, Fred was like a psychiatrist project
Right.
manager.
You had to be a psychiatrist.
He was-
He made everybody
He was
work
the
together.
Fred
staff
was
psychiatrist.
drawn from our ranks, so he understood. I mean, I always thought of you, Fred, as Mr. Powered Flight. That probably was a fairly short period when you look
It was
back
a
on your
short
life.
period.
Yeah.
But that's
You and-
what you were. So, and you were one of the guys that I needed.
Was
So
Ed in Powered Flight? Who else was there?
I just remember Fred. Actually,
I
on
want
that,
to say that from the background of people, it's interesting. In those days, we of course had physicists on the job and mathematicians and engineering graduates and students. We probably had a literature major here and there too who jumped in there. But there was no computer science discipline as such. There's nobody there who was a computer scientist per se. And,
Did they even teach computer
and I don't think they
science?
even taught it.
It was not a
Right, it
course.
was not a
Right,
course.
right.
But I often felt that part of our success at that time was due to the engineering and physical science backgrounds of a lot of those people, because maybe they weren't the most elegant programmers, okay, but they understood what a specific impulse of an engine was, or what the physics of what you were trying to do. And you weren't taking somebody who was a sort of from the inside of a computer and then who knew that, and then trying to get them to understand the problem that you were trying to solve. And I'm not saying they couldn't do that, but I'm just saying that at that time I thought that one of the reasons that we so rapidly was able to do this, I think there was a great understanding of what the problem was. And even if we had to do some fast learning, but people had the basic tools. I think that was important.
yeah, I remember I illustrated before. I remember when you joined, Margaret, and I didn't want to tell this against you, but one of the first things I did in interfacing with you was explain an inertial navigation system to you. And you were a math major, if I remember rightly. And you hadn't worked, you understood, but you hadn't worked with coordinate systems. And I spent, a couple of hours, a couple of days, going through what the basis of the guidance system was and how it worked and blah, blah, blah. I never talked to her again because you understood. And you became an inertial, at least somebody who knew what inertial navigation system and how you describe them and how you control them. So,
I want to get back to something that Jim said and what he did in that group. There was another fellow who perhaps should be here as well, who also contributed to that group. That was Bill Widnall. We needed those simulations so much because it was the only thing that grounded us to what the truth was. I mean, you could never tell what you were doing was going to work until you banged it against a simulator.
Unless the simulation was wrong.
Unless the simulation was wrong, and I suppose that happened. I don't remember.
But that's why it was
too
so
many-
important.
I don't remember too many
Simulation.
times, and I was really impressed when somebody had five degrees of freedom in the fuel sloshing module of the vehicle, and they had all the stars in the right places and all the everything else that would happen. And it was really, it became our sort of truth. And I was thinking about this last night before I came here also, that, you know, this was basically a fun project, although there were plenty of difficult times in the project when you're in the middle of it. But we did a lot of testing in this project, a lot of testing with these simulators. And I think that if all we ever did was fly the nominal mission, so that with nothing wrong, it would have been pretty boring after a while if you had this just one set of parameters and you always fly one set of parameters. And I think that part of the fun that we had was thinking up and creating these crazy off-nominal cases that probably could never happen, and then bang that against the software that we designed, and design certain margins into the software that would make sure that, you know, that if you which way or what way the gimbal would go, that, you know, you'd be able to get out of it, and other things that made such variety in the testing, that for one nominal case, you know, we ran 100 off nominal cases.
No, also an advantage from a computer science or software engineering point of view of having different missions is that we learned all about the advantages of things that people don't think too much about today, like reuse, and how that could cut down on testing, or, you know, we learned all the things about what it means to manage these different missions, what's reused between the LEM and the command module, between this mission and the one that's going next. How do you evolve? How do you do it in a reliable way? In other words, it was a great place to learn about how to do things the right way. So that was...
No, the whole thing had to be structured too. I mean, all that software had to be, we structured it into programs with numbers. We called them things. We had names for them. The astronauts eventually picked up some of those same names. I mean, they would get into P40. I mean, they didn't know what P40 was. These things were not that those names were so great, but the fact of the matter is that software all had to be structured and organized, and there had to be a nomenclature on it, and had to be interfaces built.
They took on a life of their own.
It took on a life of their own.
Banks manually here, there.
Right.
And it had to be ready about, 8-10 weeks before flight time. You couldn't change it after that.
At least.
And also we learned about how important it was to prioritize as to what was most important.
Right.
Because there was so little room to put the programs into that you would learn to delete what was less important. But prioritizing became something, and backup systems also became something that you lived your life later by doing things like prioritizing and doing things like having backup systems. I mean, in your daily life, even going to the grocery store later on, it was such an influence. But we had a Black Friday. I can't remember what Black Friday was. I just remember we were deleting all kinds of things because something more important was coming in. What was it?
Call those sessions where they cut.
Yeah. So.
I think they called it like Black Friday.
Yeah. But we deleted an awful lot because something really important had to be done. Maybe it was backups or I don't remember now. I wrote about it, but I can't remember what I wrote. I have to go back and find it out.
I'm sorry to have to leave, but thank you very much.
Ray, nice to see you again.
Good to see you, Ray.
Ray, were you the guy who...
Excuse me, come on, sorry.
Ray, were you the person who inflicted banks on us, so we had to worry about it?
That was a solution to a very bad problem.
It was a very bad solution to a very bad problem.
Well, that solution exists today in Windows, right? Or in the 8086 architecture, because you still have to do banking in order to get the extended address fields and things like that.
Right.
It's just invisible.
They do long calls.
Layers of
It
software.
drove us bananas, I'll tell you that. It was almost like area codes, I would say, in the telephone system. I mean, you had to be able to address this with the addressing, how many bits you had for addressing, and in order to get unique addressing, you had to mark it with another set of another field that would let you address uniquely, and so you had to manage that other field, and that got very confusing in the software. That was a difficult issue.
And the erasable memory was so small, what was it, 2K? That certain of it was permanent, but a lot of it, like you used during burn. And when you were done burns, that same area was used for something in a later phase. And so these phases were sequential, and all the previous information was gone and not used anymore. So you didn't have unique.
You can see there were a lot of things to do with interfacing correctly, and therefore we had the opportunity to make a lot of interface errors because we had to squeeze everything into such small space. But also, it's amazing what one could do with so little space, and how little one can do with so much space today.
Yeah, one of the things that I have remarked on to myself over 30 years since then is, at the time, we wrote software into a machine that, by today's standards, would be a very advanced architecture. I mean, we had, you heard it all the time, preemptive event-driven executives. I mean, I've worked with people who said, "What? You programmed into one of those? A real-time control computer with event-driven asynchronous?" We don't have that today.
With autopilots and jets sending signals left,
Multiple
right,
levels
boom.
of interrupts and control.
Man-machine interface, all of it. I
We
mean,
invented it for this job, and it hasn't re-emerged as a standard of computer design today. Surely there are interrupts and stuff like that, but they were not used in this coordinated fashion that we had then. Something else that we invented, and it saved those guys funds on the moon, was the software restart, which allowed, in reaction to any kind of failure, for the computer to retrack back to its last known properly coordinated state and to move forward.
You don't have to do Control-Alt-Delete.
No, this thing set, what do we call those things?
Restart points.
Restart points as it went along.
And Dan was the father of that.
I was going to say, this guy and Woody Vandiver, Dan's the father, Woody was the guy that put together, and I advised that Woody should be here. But not only did the software restart concept, I think, rescued the LEM from failure just about to touch down. They were also a terrific help in debugging this complex piece of software. We used them.
Oh,
Remember that?
Yeah.
We triggered restarts because if this thing was able to go over the same piece, we could change things and rerun chunks using the characteristics of the software itself. And I think Margaret probably remembers more of that than I do. But I remember, if we did not have that, testing of this real-time software would have been a hell of a lot more difficult.
Well, you brought up something that was really interesting, because people today, when they use computers, they try something, doesn't work, they try something out, again, doesn't work, and they just have the computer at their disposal. We could only put in runs overnight. So you'd have to think very carefully, because if it didn't work, then you'd have to wait till the next day.
You wasted a day.
A whole day. So then what we learned to do was to find a way to run like 100 runs at once, thinking about it before the fact, and the restarts remind me of that. So you try all these different things all at once, and in a way you got more done because you had to think it out so carefully. You got done maybe more in that 24-hour period than if you were sitting here ad hocly just trying something. And so you were basically doing things more in parallel, I think, in your thinking process and your design of the test. So that was a totally different.
Yeah, I don't know what lessons can be learned from that, but we did this with cards offline.
Yeah, cards.
Punch cards.
There were no such things as terminals or interaction.
That's
As
right.
Margaret said, you got your stack of 2,000 cards. You gave it to the guys in the computer room, who by then had cordoned themselves off. You couldn't. We used to go in there and run the runs ourselves, but that At some stage when Jim's double Honeywell came in, that was the end of that.
And the thing is, if you dropped the cards, you had a real problem. But it made you realize, I mean, that was part of the reason we worked on doing something where if you dropped the instruction sets, it wouldn't matter because it was smart enough to get it back together again. That was later. But we used to take pieces of cards and say, here, put this in your deck, and that would be the reusable.
Yes.
Remember that?
You
Yeah.
had to learn to use
See, I don't know if
519.
These are like horror stories or war stories. There's probably something to be learned from this experience,
Yeah.
that the few, under arduous circumstances, were able to turn out something as complex as this piece of software was and have it work and prove that it worked. That seems to be missing today. And I don't know how to put that together, but the fewer people and the more crude the development environment was, the better seemed to have been the progress and the end product. There's a conundrum there. I'm not sure what
We
it
did
is.
something that I know Margaret was intimately involved with, and that is, I think it's written up in Microsoft's method of doing their software today, I think. But we had a nightly configuration control group that looked at all changes that were created by anybody during the day, and had to pass this little group of people, which might have been 4 people, and we had the quote,
road mothers.
we had this quote advantage of doing an assembly every night, so that these changes were brought in to one listing, you might say, and then by the next day you'd have an update of that program. And so you had an extremely tight configuration control system. Now today, if everybody's programming on monitors and they're all distributed and so on, this is a much more difficult environment than we were in this one building, everybody producing changes and cards and write-ups of what their changes were, all being funneled to one small configuration control group who would then pass on everything that went into that system. And that was done continuously. I don't know if it started right at day one, but it was done on the flights that I remember, and it was a very effective way of keeping errors out of the program.
But there was more to add to that, in that every single day, the person who reviewed the changes would put out a memo that would go to everyone that was involved in that mission, so that they were aware of what the changes were, so that then if they had problems, they'd know that a change had been made in that area. So it was that communication, just hard copy memos that went out alongside each daily revision. That I think
It shouldn't be
helped.
forgotten that this was an assembly language program.
Yes.
Yeah.
And if somebody had set up a simulation with what we call special requests addressed to certain locations, and somebody changed the underlying stuff, the locations could move and that simulation run would just be incorrectly formulated, as it would turn out, but that would take a day. And so you had to be careful not to kill somebody by shooting down something somebody else was planning to do with a fixed configuration,
Exactly.
which was never fixed because somebody had to change something every day. Towards the end of the development of a single mission program, and this is a fascinating thing, it's been mentioned that NASA let us do just about anything we wanted to in the code. We did have some help from a famous guy at TRW, but basically we were completely given free rein until we delivered the software to Raytheon to build the core rope. And then we would go into a series of tests with absolutely fixed configuration. The purpose being to find any more bugs that hadn't been found. And sometimes when you sometimes you would find bugs that just you felt had to be fixed, and usually they could be. But once the program was delivered, this group of people who were the only people in the world who NASA thought could write this software suddenly were so stupid that no change they proposed could be plausible at all. And so anything you suggested, the answer was no. And you had to beg and so forth for the interest of the project to be allowed to remove this desperately bad thing. And I remember one night in the LEM1 software game when one of these showed up, probably with a digital autopilot, which was new. And it was late at night, it must have been 9 or 10 at night. And I called the guy, and I'm not going to mention any names for reasons that you'll see. I called the guy who was monitoring us at NASA at home because I had to get his permission to put this change in and to let him know it was coming. And his wife answered the phone and said he was at work. So I called him at his office, and nobody there. Well, I knew that this guy wasn't always telling his wife what he was up to say the least. And here I was with this problem. It was 10 o'clock at night. We wanted to put this change in. It was, in my mind, whatever it was, really important to put this change in. I knew the guy wasn't where his wife thought he was. And I didn't know what to do. I couldn't leave him a message at work because they didn't have voicemail. And I didn't want to call his wife back and say he wasn't at work for fear of what would happen to him when he got home. And what do you do in a case like that? I mean, we were absolutely at the mercy of getting approval of those things. I don't remember what happened, but
He was in the bathroom, no.
I doubt it. But there were some funny situations like that. Many times the software was changed after the rope had actually been built, and they would sometimes have already potted it, and they have to depot it and change the wires and so forth. It was an incredibly small and arduous process to go through. One of the things that I think deserves mention to illustrate the frugality that went into the design and the software was that the guys that invented these interpreters, and we had a second generation of them later than the one that Hal Anning had developed, realized that single precision was too small to do Earth-to-moon navigation, but double precision was adequate. And so the interpreter would do everything in double precision, or lots of things in double precision. It was a ones complement machine, which was funny enough by itself, so that there were 32,767 states, not 32,768 states. And unfortunately, there were some optical encoders on rotating gadgets that needed 2 to the 15th exactly, and not 2 to the 15th minus 1. And so it also was capable of doing two's complement arithmetic, which caused some other problems. But here we had a ones complement machine with 2 forms of 0, and double precision in which the interpreter was perfectly happy to let the 2 parts of the word have different signs. So you could have a +1 over here and a -½ over here, and the result would be whatever it is, +½ And that was clever because the software to do sign correction all the time, took space, and was eliminated. Unfortunately, however, there were a lot of cases where that just turned out to be a real pain in the backside. Mm-hmm. And there were lots and lots of little bugs that showed up when there was sign disagreement in a way that somehow got through all the checks. And so there were things that we did to ourselves sometimes in the interest of frugality, or needed to. It was a different day. It was a different day. Dan, of course, solved the assembly language problem. He solved lots of problems. Wrote an assembler. We had an assembler on the Honeywell machine, which was a batch assembly. You would take all of the assembly programs that you were going to update, and you would assemble this huge deck of cards that would affect all of them. And one of the characteristics of this assembler was designed for a tape machine, so it tapes up and down and so forth, was if your cards were in the wrong place or had the wrong number on them, they wouldn't go where you put them in. And they wouldn't necessarily even go into the program that you had them aimed at. And so you had to meticulously check your assembly listing in the morning when you got it to see if all your changes went in there. And if they weren't where you expected them, you had to go try to figure out where did they go. And it was an arduous process. And a careless person could wreak havoc on the world in those assemblies. And they would run for a long time. The saving grace of the Apollo computer was that it was slow. And why I say that was that the simulations that we did and the assemblies that we had to do were very long. And if the machine had been 10 times as fast, it would have taken 10 times longer on the best hardware that we could buy to simulate this stuff. And we would never have been able to run these simulations. They would have just taken more time than we could have possibly had. So sometimes the limited resources are a blessing in disguise.
That's why those
simulations ran-
emulators people have on today's computers have so much trouble. They're trying to emulate something that's so fast.
Yeah, that's exactly so. We had things in the simulation called clock advance, in which you tell the simulator you were willing, when nothing was happening, to just jump the clock up to the point where something happened. And the simulator would figure out when that was
Yeah,
and
that's
just take a
great.
leap up there.
I really
And it
like
really
that.
advanced the speed of the simulation to the point where it was nearly real time in a lot of cases, depended on how busy the computer was. But there were lots of periods where it was just idling and maybe a few instructions or maybe a few seconds. But it would just leap the clock forward. And that, as far as I know, never caused any difficulties, because we didn't pass anything where if an interrupt happened, that's where we go, or something else. There were a lot of tricky stuff in there.
I keep telling people what that simulator used to do, and they can't believe it. It's many things it did that people don't do today, that they should do.
One of the fascinating problems was the reuse of erasable memory. And like every memory problem, a piece of software that would use somebody else's memory would likely get away with it, because if it started writing into that area and then completed what it would do, it would go away. And then the person who had left something in there for its use when it came back would hit something that somebody else had written in there and go completely wrong. And then by then, the real violator was long gone, and you had to figure out who did it.
Who done it?
And there were also problems of using erasable that hadn't been initialized the way you thought it had. And we came up with a technique to put kind of random number into all of erasable when we started.
Background.
And if that was ever hit, you could see it. And we had a way to put that same random number back in so you could do kind of diagnosis to find it. There were just things that nobody does anymore.
You know, they still haven't
Yeah.
solved that. You don't know how many students of mine, like now, their programs only work when there's 0 in the
Yeah.
location
Yeah.
when they start. That's the worst thing I've decided that you could put in unused.
Yeah,
But
that's
why
right.
aren't people doing these things? There are so many things that would really help debug systems today that never were brought forward. Many things are, but that was one that was, I think, more advanced than most debugging tools we have. Why do you think that is?
Was there any effort to kind of disseminate in a systematic way the kind of knowledge and programming that you gained within that project to kind of flesh out the most important principles that were worked out in the work of this project and kind of published them?
There have been a few summaries of the program that people have written volumes. I think that you probably have gotten your hands on. I know there was a late volume written by that woman, Madeline Sullivan. And sometime she wrote a multi-volume history of Apollo. I think it was one of the lab documents. But I don't know that anybody has tried to record the essence of, let's say, programming breakthroughs or programming inventions or something of that nature, or the salient discoveries, if you will, in the Apollo. I haven't seen anything like that.
No, I don't think so. Some parts of the engineering have been covered with some good papers. Well, Batten's got a book, but that's more theoretical. But haven't there been some papers on LEM's autopilot, lunar land?
Perhaps
Bill Windell wrote a book on the autopilot.
Right,
I think it was the CSM autopilot, but
right.
published by MIT Press.
That's vaguely coming back, maybe that's.
But
what
not too many people were thinking of publishing. They were trying to just get home. I mean, I don't know how many people were working 6 or 7 day weeks, 80-hour weeks, and doing everything they possibly could in their power to get these guys to the moon and back.
A number of marriages sank during that period, including mine.
I think there was an element in this program that is missing in a lot of current programs. The 60, 70-hour week that we just spoke about, I'm sure that people do that today too, but there was I don't know how to say this, an immediacy or a familiarity with the astronauts. I'm talking about people at MIT, but it's probably true in other parts of the Apollo program, that you felt a certain personal responsibility to either you made promises or you had conversations with these people, or you were doing it because you wanted to make sure that there was absolutely zero errors in this program because you knew that their lives were at stake. There was some sort of connection to the astronauts that I felt, and I think other people at MIT felt, perhaps because they came there for training, or I know there were occasions we went to dinner with Doc Draper at Lockovers with some of the astronauts after a flight, and I think that affected kept morale up and kept people's attention and feeling of dedication to the job because of that sort of connection.
Right.
You weren't working for some big bureaucracy. It was this. In my case, it was sort of a feeling that some sort of connection with Chris Kraft that you were satisfying his leadership, you might say, plus this feeling, this sort of feeling of the astronauts. I would say that certainly affected me in the job.
Absolutely. They were here. I mean, which Apollo flight had Jim McDivitt, Dave Scott, and Rusty Schweiker? That was Apollo 7, 8, whatever. but they seemed to be around frequently before that, and you just seemed to see them doing this stuff and get to know what they were doing all the time. It felt very close. In fact, we used to laugh at them picking on Dave Scott. He wasn't quite as fast as picking up the stuff when you showed them that. But they were there frequently. But even before that, I remember the first time we went to Houston and gave a presentation to a lot of them. That was earlier still in the engineering mode. I mean, these guys came out and they didn't just sit there and nod off. They were excited and asked. I remember Neil Armstrong overwhelmed me with the questions he asked and how well prepared and how thoughtful. And I said, geez, these guys, there's no fooling them. They know what they're looking for, and we better be really careful at what's going on here and make sure we're prepared. When they ask questions like that, you can't wing it.
Was they actually interested in software as such?
Some were.
Not per se.
But they wanted to know how this worked and what was going to happen and what it meant to them.
And how they worked through the controls, but a lot of the controls were driven by the software. So what they said or didn't say had an immediate impact on us who were making those things work in the front through the software itself. I remember Steve Copps there was the man, I've forgotten what the hell that thing was.
Oh, you should mention
the astronaut document that gave the whole sequences of all of this.
Right, that worked for John Dolan. What's the name of it?
The GSOP, the Guidance System Operations Plan.
Steve and Malcolm and Jack Shillingford all cranked out all that stuff that went on and on and on.
This is the first time I'd ever seen a specification for anything. And today, you design the spec first and the software falls out the bottom. But those GSOPs, I remember John Dolan was the guy, remember him?
Yeah.
The man with the 8 kids, I think, who lived in the South Shore somewhere and came into work every day.
That was a thankless task, turning out all that stuff.
Yep.
And you had to get it all.
Because he was,
And
the
and they had to
astronauts
run
and
down and
NASA
catch us
and
to
us.
get,
Yes.
every time they had a question.
Oh,
And they'd
John,
start,
don't
can I
be
talk to you a minute?
Yeah.
I still have something like 280,000 Eastern Airlines miles that are now part of the Continental system that never expire. And these
Look
were,
out.
These were on these multiple trips.
Midway is already thrown in the towel. Who's next?
Multiple trips to Houston, but one of them I want to just bring up in the conversation here. I don't know how many trips we all made to Houston. I mean, and I can remember, I mean, I can just see myself having this heated discussion for an hour and a half between Boston and Atlanta with Margaret on some programming issue or something that we were doing. But we attended innumerable meetings down at NASA, and we had a very live wire at NASA who we went to see all the time, and that was this guy, Jack Garman, who really was, he really, if there was anybody at NASA who sort of understood what we were trying to do, it was this guy, Jack Garman. And
I think I always felt like Dr. Frankenstein, that I created a monster.
Yeah,
he got assigned to me, and for 6 months, an hour a day, I keep
he was
telling him this stuff, and
like
he
a
was persistent. Phone calls.
But I remember this day, this particular day that I had finished a meeting at NASA and was coming home. And we were standing, I guess, walking between the parking lot and the terminal. It was sort of like a driveway that headed up toward the terminal in Houston. And I can't remember whether this was Hobby or the International. I can't really remember. But anyway, everybody said, well, wait a minute, there's the president. And so we watched, and this open car came from the terminal past us. And there weren't very many people standing around, maybe one deep along a road that might have been a half a mile long. And he rode by in an open car with his wife at maybe, I thought it was around 15 miles an hour, but nothing faster than that, maybe 20. And I remember standing there, I don't know who was with me, and I said something like, you know, if anybody wanted to kill this guy, this would be pretty easy, because he's just rolling by in an open car, and so on. Well, that was November 21st, 1963, and I think it was a Thursday, I think, and I was coming home, and I was in my office the next day, and he was no longer in Houston. He had gone that night, and then he went to Dallas the next day.
Yeah, I was there that same Thursday. I think it was a different meeting, and he went right down. They hadn't built the MSC yet. We were in Houston. It was the Office Park, whatever it was called, and he went right down the main highway there, although we didn't go out and see him. But I stayed over till Friday, and then Friday I was heading to go home, and at the airport we got all this news.
But do you think it was a Friday?
Yeah.
Yeah, that's my recollection.
Yeah, but Thursday he was in Houston and went up and down whatever the name of that Gulf Freeway or whatever it is. There was a parade or something. And then Friday, I stayed over Thursday night, some more meetings Friday morning, was heading home Friday afternoon. And in the Hobby Airport, we heard the first news that all of this had happened.
I wanted to touch upon this religious war I mentioned before and get into it just for a moment. The issue really came to a head in the shuttle program, where there were forces that believed in asynchronous, priority-driven, interrupt-driven executives, and other forces that believed in absolutely synchronous executives, where you planned out all the software and you executed the software by tables, and you could tell what part of the software was operating at every instant of time, because you had planned it out so that it all operated very rigidly. And the people who really used those kinds of executives were mostly people in the aircraft industry And they had come from various airplanes where they had these computers and they had these synchronous executives, and it was very important for them to know exactly what was happening at every instant of time, either from a testing standpoint or whatever. That was their mindset. And the people that had worked on Apollo, for the most part, believed in this asynchronous executive where you had priorities and you didn't have everything structured completely, but you allowed higher priority jobs to interrupt lower priority jobs and so on. And there were these incredible discussions in the early shuttle time, in deciding what kind of an executive should be used in the operating system, should be used in the shuttle. And the shuttle had its own hardware issues with multi-reliability strings and an I/O processor and other things that had to be synced. And so they had a lot of reasons why this was a big issue. But the roots of the Apollo viewpoint really stemmed back to the alarms that occurred on the lunar landing. And as you recall, in that flight, when that balloon was coming down, and all of a sudden he had these alarms, and the astronaut kept getting these alarms. He said that he had alarms, and finally there was a decision in Houston to just push on and that he should land. And whoever made that decision, Steve Bales or whoever it was, either he understood what the problem was or he felt that he
Well, Jack Garman was screaming, I heard him, go, 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 go. And I don't think he had any evidence other than he thought we had restarted it perfectly.
At any rate, he landed safely, and following that landing, there was just a frantic session at the MIT lab to find out what in the world was causing these alarms. And it took us the better part of 24 hours, I think, as I recall. And going back to the simulators, we simulated this. We tried everything to make this happen, and we could not make this happen. And it was as if the machine, the AGC was operating at about 25% slower than it usually operates. And so we tried lots of things, and we couldn't make it happen. Eventually, over the suggestion of somebody who worked at the Cape a lot, we tracked down the fact that they had a switch in the wrong position, and it was stealing cycles, and there was a radar rendezvous switch, and that made the AGC run slower, and because it was running slower, it was dropping low priority jobs and not getting to these low priority jobs and only doing the highest priority jobs. And so the job queue filled up, and when the job queue filled up, it caused this alarm to go off and so on. And at any rate, MIT got a lot of criticism for software error causing this to happen. And so now you had a sort of a dichotomy where people believed that what had happened was actually an error, and other people believed, no, the software actually saved the program because it, in the face of this mistake in the switch, the software, which was written as a priority executive, was able to go on with the highest priority jobs and not tank the mission because it didn't have to do this boxcar structured synchronous system where it would give time to everything, whether it was important or not.
Well, you know, it was even more complicated than that because the error was in the actual documentation.
Yes, I was going to mention that in a moment. But so this feeling went forward, including the NASA folks, people like Jack Garman, who absolutely felt that it was important to have such a system in the shuttle, versus the airplane folks who felt that they could never be able to test the software afterward if they couldn't have an exact match and knowing exactly what happened at any time and the asynchronous executive was almost not repeatable, you might say. So that caused a great deal of difficulty. What Margaret is pointing out is that when we finally got and found, I remember the instant that we ran upstairs,
Russ Larson.
to look at the telemetry to see where the bits were set. And sure enough, the radar's bit, the switch, the bit, which was picked up by telemetry and downloaded, that was in, let's say, 15-bit, or how many bit words they were in the telemetry, and bit 9 or whatever it was showed that the switch was on.
Rendezvous radar.
Right, which meant that's what it was. And eventually the ground told the astronaut when he was about to take off from the moon, to put the switch in the right position, he said in a very low-key fashion. But when that was run down to the end, it was found in the crew procedures to put the switch in this position. So the next question was, well, how come if you put the switch in this position, wasn't this picked up in the simulators at Grumman, which these guys had been training on for, I don't know, a couple of years. And in that crew simulator, they had always done exactly what was in the document, put the switch in that position. However, that switch wasn't connected to anything. In other words, that switch was not connected in the simulator to the AGC, which would slow them down in that simulator.
You mean at Grumman?
At Grumman. So they trained exactly to what those crew procedures said each time. And they did it on the landing too.
Well, it kind of gives you an understanding more of how important everything is with respect to the entire system of software, peopleware,
Then I can put it the other way. Why didn't our simulations follow the crew procedure?
I don't know that the crew did that in our simulations. I don't know. It probably didn't. I don't think it was in our digital simulator.
It would have been if we turned on the rendezvous radar.
I don't know.
But when you're testing, back to the system thing, what would make the software do something like that? In other words, you begin to think in terms of modeling and designing a problem and where do you stop? Where's the outside of the outside? But it's modeling all these things as one system of which part is realized as software, part is peopleware, part is hardware. But then you begin to model it as an entire enterprise and then simulate it as an enterprise. But it makes you realize that when people blame something as being a software error or a hardware error, you're not necessarily sure what is it and what does it mean to be a software error or a hardware error. And this brings up all these questions when you have events like this take place. And we've still not solved it today. I mean, in the industry.
So did they stick to that asynchronous design in the shuttle program?
Did they stick to, excuse me?
Asynchronous executive.
I think that they had a mixed system.
It's a hybrid. Yeah.
It was some sort of a mixed system. They had some hardware constraints on their I/O processors and the synchronization of I/O with the computer that made it impossible to have, I think, a purely asynchronous executive. So they had some real hardware issues involved in it. And we in the company that we formed after we created a programming system for shuttle in which we built into the programming language the concept of asynchronicity. That is, that you could have multiple jobs and priorities and interrupts and things like that. And the shuttle people, for the most part, didn't want to use those features that we had put in the language. We were very influenced in the language by the experience in Apollo, and so and very influenced by the executive that Hal Lanning had designed, and the manner in which he had designed that whole thing. We were very influenced in the language design to take advantage of those things, of which they were, I would say, used to a minor extent in the manner in which the shuttle was put together.
Maybe we would make a little break, 5 minutes, or we're changing the tape now. And then and then we'll continue for about 1 hour, because we started at 10. It's fine. And,
That's fine.
Okay.
All the time on our Apollo, we had just about no contacts with the military. The military has its own, we're worrying about military satellites and so on, but our paths just didn't cross. I don't know if Shuttle is where they finally came together, but not on Apollo. There were a big difference between the people we dealt with in Houston and most of NASA and Langley and the old people versus Huntsville, Werner von Braun and the German gangs down there. They did things a little bit differently, and so there was a lot of difference of opinion. I mean, they built things in a certain way, which was very, very
But with all due
solid,
respect to
methodical.
with all due respect to Jim's time in the service, I think there was an actual disdain for the military in this program. I think that you were afraid that the military getting sort of some sort of influence on the program in some fashion. And you were very happy that the program was completely open, and it was open to the public, and it was you could talk about it, and
Well, there were certain aspects that still had the stamp of the military on. Some of those inertial instruments and stuff were still classified documents, if I remember right at the beginning.
is that right?
Trying to get some data,
What about
because they sprang from Polaris and things.
were the computer instructions classified?
Not that I recall, no.
The only thing I remember being classified about the computer was the oscillator frequency.
Because I wasn't able to get a hold of the Block 1 instructions because of some reason. I thought it had to do with being classified, but when I first came in to learn.
I think ossified is.
Was it ossified?
Ossified.
You have
Do you
to.
remember that, Dan? You weren't able to give me, or Alex, you couldn't give me a document because it was classified.
I don't remember that
just don't
exactly, but I
remember.
know
Yeah.
there were sort of source documents that were classified.
So you had to write down, like I can remember, you had to write down a few instructions to say, here they are.
But didn't we have safes in that building? I remember, I can
Yeah.
picture the safe.
Yeah.
What, I can't remember what I kept
What was in there?
It was definitely a classified area.
Yeah.
Yeah.
Was it
Having
the-
to do with the inertial
I thought it had to do with the rocket.
I don't know.
You can see how much we were influenced by
Did you have to obtain any security clearance or something?
Yes, we all had security clearances.
Yeah.
But I don't know whether
Nothing
security
we ever
clearance-
wrote was classified, though.
was
My
unclassified.
security clearance was initiated in the Polaris.
That's where it
program.
came from,
And
yeah.
I think it was kept going from that.
Right.
But then I had to get one.
Oh, you had to get one?
Yeah.
Interesting.
I don't know.
I had one.
Although
I think I had
actually, I
one,
had
but it
one
didn't
from the
work
SAGE
out.
system, so maybe mine was left over. I don't know.
And so you didn't have any sense that the military were interested in at all in kind of innovations that went on in your project?
No.
We never thought in terms
Only
of the
military person I
military.
can associate with Apollo was General Phillips, and he didn't exactly come around looking over our shoulder.
No.
I don't know, I think that's a little too strong. I don't know that we knew that they weren't interested. They just were out of sight. They just weren't.
Visible.
They just weren't part of it.
I think they just thought we were gonna totally flop, so why did they want to talk to us?
Yeah, going to the moon was a political thing, not a military thing. So
Yeah.
there were no objectives of the military involved in it. They weren't going to the moon.
Well, they may have been, but they didn't.
It was an ego thing.
Yeah.
I mean.
It might have
we were
been an
supposed to-
edict. It might have been an
because-
edict from the president.
Yeah.
You know, that this is an open program, that this is a big political show for the world, that we're
Right.
going to have everything, you know.
Because Sputnik happened, so we had to
Right.
go and,
Contrast it with the Russians, you know,
Yeah.
they're in the middle of Siberia and nobody knows what's going on, and here, this is completely open.
In Russia, there was always a kind of a rule that either significant invention was made that might potentially have military significance, they would classify it, even if it was done within some open program initially. But this here doesn't seem to be that kind of oversight in the sense of military searching for things that are going on that might potentially be important.
Well, there's a big danger in that, because the military, it seemed to me, and the people who were in charge of security had a ever-expanding horizon. I mean, you'd have everything being classified because you couldn't tell whether this little gizmo might have military significance. So after a while, you'd wind up with almost everything.
That's what the Russians want.
Yeah.
So I'm getting a sense that there was a lot of kind of interaction in small groups while working on those programs. Or did you have mostly kind of one program, one programmer, or several programmers work on one program? How kind of knowledge about what
Maybe
was in
4
the
or 5
program
on
was
each
shared?
functional area.
Well, you had different areas. I mean, if somebody was working a navigation module, they probably did not have too much contact with some people who were working in powered flight. So they were worried about star sightings and covariance matrices and things having to do with navigation computations, and somebody else was worried about autopilots and how they were going to fire engines and so on. And they were aware of each other, but there may not be very strong interfaces between them. And these two groups, I would say they might be, you might have a powered flight group of maybe 6 people and a navigation group of some other number like that. And you had people who were testing, and you had people who were writing and specs. And so I'd say you had a lot of programming groups. So when you add it up, you get to the numbers we're talking about. But each group was a somewhat contained group.
Yeah, there was the parallel group of analysis guys that sort of were writing Mac programs all the time, testing algorithms and so forth. They weren't really writing software for
Yeah, I was going to make
guidance
that comment
computer.
because
That's right.
programmer was not, a job description. Some people programmed and did analysis, and some people only did analysis. Somebody did all the work in Mac, this analytical programming language we had. I've got the brunt of that because I remember in trying to put this first flight program, of which I was the inaugural rope mother, together, I had to interface with these groups and make their stuff meet the stuff of the next group. I remember putting the launch people stuff, which was just plain analyzing dynamics and finding out where we were, to the powered flight people who steered the thing and took over the mission at that point. Then it went into this mid-course thing with some of these star sighting people who were wacko analysts. I mean, I didn't understand what. I still to this day don't really understand some of that. That was a whole different regime because here 10 minutes was a short time to these guys, whereas 1 second was a lot to the powered flight people. And then I survived going through that mid-course stuff, got all their stuff straight, was able to then power up this guy who was the entry. He'd been working this way. And I remember the first day our simulation knitted these two phases together and we got a coordinator. So these guys program, Dan and Ray's program, and Fred and company, and some of the other, and all my glue that I had hung this thing together with actually worked. But there were a lot of different programming styles and conventions that you had to straighten out. These guys expected their delta V's in some, we were giving it in the wrong one. You had to, this kind of thing. So putting these cells together was an integration job. We didn't integrate at the beginning. It was not a programming exercise for the whole mission. There were these analytical groups, some who did programming, some who didn't. Different styles, there were no standards. All that received a lot more discipline and method.
It's remarkable that you had
later.
That we didn't have more interface type errors because we did have no standards. We had no programming standards. Each group or each little entity would have a style. I think when we got this project management, I did try to some extent to get some standardization, but it was hard. I think people use different expressions for constants in their programs.
Yeah, but don't forget Don Bowler and the stuff he did with ICDs. I mean, that, if we hadn't had a function like that with all of the specs from all of the other vendors as well as our own, we would have really been up a creek. I mean, that was absolutely
Who was that?
critical. Don Buller
Don
did all of
Buller,
the ICDs.
yes. Big Don. Another guy I remember, even bigger, Peter Peck,
Yeah, he was bigger.
who instituted control over revisions and stuff. I don't know if that group that you said that took over, wasn't that Peter's group?
Well, he started
I
early
mean,
when he did it
but this
all
came out of
along.
nowhere. He thought this needed to be done, and he started doing it. I mean, there was no the configuration manager.
Oh, Peter Peck.
Peter started that kind of stuff, and he'd come and argue with you. You couldn't put changes in that day and stuff.
Sit on him.
Sit on him. Yes. He was a very large person.
You don't want him to sit on you.
I know what this is.
But we invented that in the course of the work. That kind
There
of
certainly were integration problems outside our building. And I think that our experience within the building, and we were all within a building, which wasn't that big a building, were relatively well controlled. But some of the interface problems we had that were experienced between our stuff and other people's stuff and between various other people's stuff. I remember, for example, was it 501, Dan, or 502, where there was an engine failure and the software, nothing to do with us, shut down another engine thinking that they were shutting down the one that had failed, and so it was down 2 engines out of 5.
Right, we ended up in orbit, and they were supposed to do a translunar injection, but because of the failure, they didn't have an S4B left or whatever it was. We ended up, instead of on a trajectory headed towards a translunar, we ended up either in orbit or an elliptical thing. So instead of doing a burn to knock us out of a translunar trajectory, we burned first to put us in, then we turned around, knocked us out.
That was one example of one of these integration problems that woke up a lot of people. I think the accident on the pad was probably the single biggest disaster that woke people up and stopped the project for, what, 1.5 years or something long. Investigations were done and Block 2 was invented or hustled into place. The mission that I was involved with, which was subsequently called Apollo 5, which we called Apollo 2, or didn't call Apollo 206, it was just 206. First flight of the LEM, which was unmanned. And
This is the flight I think I mentioned the last time. Is this the one that it was at the Cape and the engine shut off in 2 seconds or 4 seconds?
well, I'll mention a little bit about what happened because I think it was revealing. We'd never flown a Grumman spacecraft before, never guided one. We'd never flown a Block 2 system before. We'd never flown a digital autopilot before. So there was a lot of new stuff, and its rope mother was new, and we had a lot of veterans and a lot of other people that were new. And our relations with Grumman were different than the relations with North American.
Were they? Hoeg talked last time about it.
It was just a whole different ballgame. And I, for one, had never had any contact with the mission control people and didn't have much as it was. But I went down there to one flight procedures meeting. It was run by the guy who was going to be the flight director. And let me not mention his name, but it was a terrible meeting, I thought. I mean, the guy was so arrogant and obnoxious that people just stayed quiet who probably should have asked questions or spoken up. But in the event of the flight, we had the first burn scheduled, and although we'd simulated it lots of times, when the command went to the engine, unknown to me as the mission program guy and as the simulation guy, there was a lot of pressurization of tanks and stuff that took place between the fire signal and when the engine actually lit up. And I had been told by the guy that wrote the descent burn software that it had to have a very narrow window on the startup because of something or other. I don't remember what, but we had a fairly narrow window in there, and it was the timing of the interrupt and so forth, it just missed reaching the delta V threshold by milliseconds, if I remember. And so we shut it down. The software shut it down. And utter chaos took place in Mission Control Center. I mean, everybody was climbing all over everybody to find out what happened, totally preventing anybody from finding out what happened, because managers were insisting on knowing stuff that you didn't know yet, and it was bad procedure, and I don't know if that continued on other flights, but it certainly screwed up this
Jim, were
one.
you at Houston then?
Yeah.
All right, this is...
But let me go on.
Go ahead, I'm sorry.
We had put in there, as a part of the mission software, a very clever and fairly extensive ability to reprogram all of these burns. And when we, through the hierarchy of Jack Garman up to the flight director, told them that we could easily reprogram this thing and try it again, the answer was, it's no longer within telemetry coverage. Somehow they had designed this mission, unbeknownst to us, in a way that there was no possible way to use this reprogramming stuff if anything went wrong. Of course, was the only purpose for which this reprogramming software was in the flight computer. But there was no telemetry coverage if the mission didn't go exactly perfectly. And of course, there was no need to reprogram it if that's what happened. So here we were out of telemetry coverage. And then they decided to use the LEM abort guidance system, AGS, to do that burn and drop the thing without any knowledge of the guidance software. It took control away from the guidance software, gave it to the onboard, the LEM abort guidance system, which fired the descent stage, separated and did an ascent stage burn, and then they handed the control back to the guidance system. Well, nobody had ever planned or thought that that would happen. And the guidance system on, our guidance system on the LEM, knew that it was in the descent configuration. By then the descent stage had been thrown off. And so the digital autopilot had this little sporty vehicle when it was, thought it was controlling this massive thing. And so it was doing horrible limit cycles and burning fuel like nobody ever saw. And they said, what's going on? Well, I knew right away what was going on. Nobody, of course, had asked MIT anything when all this was happening. They just knew better and took over. Of course, as I thought, they didn't know better. But I, again, sent the information up that if they do this heat soak thing that we had put in there, that the first thing it did was to check agreement between the bits that indicated what stages were present and the configuration the guidance system thought. And if it found a mismatch, it would correct the situation for the guidance system and then pop out of this program. So it was a way to get the thing back in sync with one uplink command. When this was made known to the flight director, he said, we can't do that program. We've never run it in our practice simulations here at Mission Control. And here was this thing that we spent a lot of time putting in the, here was a second thing in the flight software that couldn't or wouldn't be used by the mission control people. Well, the result was not good, and we took a lot of flack for that. I think a lot of it undeserved, but I think it really shook up the mission control people who realized that their abilities to handle things was much lower than they thought, and their ability to understand and deal with the possibilities of what would go wrong in the flight computer and in the system other than that was completely undeveloped. And I think they went through a lot of learning and made a lot of changes that led to the success in things like the lunar landing, where something really unexpected came up. And there were people there who were confident enough, or foolish enough, whatever, to say, go, whatever it was, but it worked. But without some of these blunders that happened, I think there would have been a much worse outcome. Could have.
Let me ask you, did the clever things that you had put in, were they known to the mission controllers?
They were in the GSOC, they were in the software, they tested all this. No, our contacts knew that they were in there. It wasn't our job, and we didn't have time to do anything that wasn't our job. We didn't have time to do things at work. I was working 80 hours a week during
Sure.
that time. Aaron Cohen kept saying, go down to Grumman and talk to them. When? Who's going to do the configuration control? I would stay there till 8 or 9 o'clock every night looking at the changes to the listing to make sure that the assembly was successful. Usually it was. I didn't have time to go to Grumman. It would have stopped how many people were working and putting restarts in. But it just, we ran out of
When
time.
you were down at there, that was one of the only launches I went to. And I was at the Cape at that time. And when that happened, I was telling the group here last time that there was a lot of finger pointing that occurred on this narrow window you were talking about as to whether this was a programming error or whether we were programming exactly what the engine, we were programming that to the characteristics of the engine that were given to us from Grumman. And there was a lot of finger pointing as to whose fault it was. And of course along came Doc Draper, who was down at the Cape. He'd like to know what was going on. So there was this picture of this madhouse room with a listing this big, opened up to page 179 or whatever it is, and somebody sticking Doc Draper's nose into these various assembly language things, trying to talk about how this engine was cut off.
Well, that points out something else that I didn't think of, I think is worth saying. I don't know if 206 was the first mission of this sort, but it was a first, it may have been, where Houston had told us that they, not we, were going to be responsible for what we call the erasable load, which was the stuff that was preloaded into the erasable memory before launch. So the responsibility for the erasable load was ostensibly with the guys down in Houston. Well, that was fine, but for the simulator, we had to have a lot of stuff preloaded into erasable memory, and there was this piece of code called Mr. Clean, which would go clean out stuff and preload all of these constants that we thought would be fine for the erasable to start with. And people could override those and so forth, but that's what that thing did, if I remember. It was there for some reason. I remember that it was a popular commercial on the radio at the time. It happened to fit in 8 letters, and so that's what it got. But it turned out Houston never touched the erasable load, for at least for 206. And so the stuff that we had in there for the simulator, which always worked in the simulator, and Grumman ran the simulations, and I never heard anything from Grumman that said something's funny there. But there was another sort of one of these mismatches where we never saw what Houston might have done to the erasable load. It turns out they didn't do anything. But there were these interface gaps that weren't local, but they were between geographic locations that went wrong, and I think caused people to shore up the defenses a little bit on missions that came later. But without some of those mishaps, I don't know where we would have come out. But that was a tremendous disappointment to all of us that busted our tails on 206. And it was never possible to point a finger. I could never point a finger at anybody. I remember exactly where I was standing when a person who was responsible for the dips burn, I'm not going to mention his name, but everybody here I think knows who I mean, told me there were restrictions on that thing, and so the number came directly from him. I didn't make it up. So it wasn't something that we did just crazy. But, mishaps helped us a lot. The accident, of course, that took 3 lives was way beyond our purview, but had the biggest effect. Because I think without that accident, we never would have made the schedule, and maybe never would have made the landing.
Something else I remember about it was to have flown the flight program 204.
Yeah.
That program, which we were forced to release, was just so lousy, so shot full of bugs. It would have killed them anyway, is my feeling. It was so woof. It was sort of a blessing if you can call it that, that was ditched and was never used, and we went into block 2.
But it's an example of how, and I mentioned before, each program was supposed to be an evolutionary step from the one before.
Yeah.
This one had a crew on it, the one before it had no crew on
Nothing.
it. If you don't think that was utterly different, I mean, it was
Huge.
utterly different.
And I remember we had 6 weeks to turn it out.
Yeah, very short schedule. And of course, nobody wanted to be the one that caused the schedule to slip.
Yep.
We were confident Grumman would make the schedule slip. We just knew they'd never make it. Of course, they did, which caught a lot of us by surprise. A lot of good things happened, too. I remember when we ordered the first 360, Lyndon Johnson had just ensured that IBM got a sole source contract to supply 4 360-75s to the Manned Spacecraft Center, and all the other vendors were just completely up in arms. And IBM, who was the only bidder that could do this supposedly, had to supply a 5th computer because the 4 computers didn't meet the specs and so forth. It was a horrible situation. And I went to the guy down there that I had to go to say we needed a faster machine and we wanted to put out a request for proposal. And got approval to do that. We got bids from at least 3 vendors. And I called him up and I said, well, we've done our proposal evaluation, we're ready to proceed. Any problem with that? And he said, no, not any at all. He said, who is the winner of your proposal? I said, IBM. He said, oh. He said, we're going to need a lot of justification for that. So we spent about a month writing down what we thought they wanted to hear. People's Time, Cliff Hyde was the guy that wrote most of it, sort of saying why IBM was the chosen vendor. So there were a certain amount of politics in there that didn't have anything to do with us. But other funny things happened. I don't know if this is useful or not. Houston wanted to have an independent computer simulation from the one we had as a cross-check. And so they assigned somebody to write a simulator, and they wrote it in Fortran, I think, of not the computer, but some other stuff. And I had personally modified our Mac executive so that some things that we needed to do could be done by runtime software in the Mac executive that ran at runtime for Mac, that involved stealing some functions that I knew nobody or thought nobody would ever use. Like we had hyperbolic cosecant function in the language that I didn't think anybody had ever used. And so if you put hyperbolic cosecant of -1 in there or something, it would type on the console typewriter or something. And I got to look at the listing of their independent simulator written in Fortran. And right there, I said, hyperbolic cosecant of -1 to write on the console of a machine that wasn't even the one they used. And certainly not what you'd call an independent simulation. They just transliterated had this code directly into Fortran without the slightest idea of what it was doing. I thought, here we are with a real cross-check. Oh, well, we did get there. Oh, I was going to say, I lost the thread. Senior moment happens almost continually with me now. After having gotten this first IBM machine against all odds and getting it installed and stealing it from somebody that we were doing business with, and George Miller called them up and told them they were going to have to lose their machine. And it got very ugly because this company got really angry with us for identifying them as somebody who might give up a machine and so forth. It took us quite a long time to get it in and installed. And we were running lots of simulations on there and a lot of other lab stuff as well. When we realized we just needed more simulation time than there was on one machine in 1 week. So I went to Chris Kraft and said, we've got to have a second machine. It was absolutely astonishing. Within 6 weeks, that machine was running in our place. Before, it had taken probably 10 months. And he just was able to make things happen for us and for everybody else in the project that really gave it what it needed to succeed. And I think without influences like Chris Kraft, both inspirationally, because he really was a guy we all respected and liked, and without his clout, the project would have not made it. I mean, there were just lots of things that happened to come together.
By the way, he's written a recent book. Has anybody read that?
So I've seen him on TV and heard him on the radio talking about it, but I haven't had a chance to look at the book
It's
yet.
supposed to be pretty good.
But on Apollo?
Yeah, on space program and issues and he's
Everything.
very frank. And
I also read in Gene Kranz's book that the volume of Tyndallgrams was actually published and circulated. I've never seen that either.
They have some here, because Malcolm sent his packet to you guys, right? I think he sent it.
To Sandy.
Sandy. To Sandy.
Way afterwards, it must have been 91 or so, I saw Bill Tyndall at Intermetrics and urged him to publish his Tyndallgrams. And he maybe already had, but he didn't say so. He said, why would anybody want to read that stuff? And I tried to sell him on the idea, but he didn't further do it as far as I know. But I did read it from Transit. They were circulated around. Some people have. Another guy without which things would have gone far differently and worse.
Right, Bill Tyndall helps solve so many, especially at Houston down there, all drag them all together and beat enough heads, pound enough heads together to get agreement. It was amazing how he did it without any, just by dint of his personality. I'm not sure he really was the guy, the boss of any of those people, but when he said it, it happened.
Well, I remember before Bill, the ill-fated Dr. Joe Shea. Remember that?
Poor Joe.
Facile, whatever we had there.
Joe got
He got the axe.
Blamed for a lot of things
Yeah.
that weren't his fault, I thought.
But he had a style about him in conducting a meeting. Remember those facets? First article, configuration inspection. It was Joe Shea sitting like this, shirt up, red socks on his boots. He didn't. A rather unassuming guy. I was kind of fond of him and looked at him from afar. Then he was the scapegoat for Apollo. So,
in the later stages of the program, we talked a lot about the personnel and the people at MIT and good people that we got and so on, and the closeness. In the later stages of the program, it was a determination that we didn't have enough personnel, and that we needed to run this more like an aerospace program, you might say. And so there was actually an effort to bring in contractor personnel, and I don't know how many were brought in, but quite a few, a lot. And by and large, these people were very good people, and they were integrated into our efforts. But it was just another example of how something that began relatively small and close started to get toward the end look like a lot of other programs where you brought in people under different badges and different management and so on, and then you also tried to parcel or apportion them in intelligent ways, either testing or try to create tasks that they could do that were self-contained, but in many cases they were integrated into groups of MIT personnel as well. I think that by and large that we did that fairly successfully.
And in the flight software group, I think they were you couldn't even remember that they were subcontractors.
Right.
You just assigned them.
Yeah, Joe Saponaro to run that large team, crack the whip on all.
yeah,
It's been a bunch of guys from CUC,
yeah,
Yeah.
Phyllis.
and don't remember how many from AC, but if Jay Sampson hadn't been in that group, we would have languished.
Right, we did the 501 with Jay and the gang.
Romy
Jay did
Gilbert,
most of it.
remember him?
Who?
Romy Gilbert?
Oh, yeah.
Down on the, okay.
Was there any interaction between the instrumentation lab and the rest of MIT as a teaching institution? Did undergrads or grad students appear in the lab?
We hired a lot of people
Well,
from MIT.
there was close interaction about the time Apollo started, because it wasn't so big and it was closely tied with the aero department. And the instrumentation lab was part of MIT then. You remember the faculty club, athletic, and so on, like Lincoln Lab. I don't know, maybe Lincoln Lab still is. But then at some point, due to Vietnam protests, the lab split off. I don't remember, early 70s or
69,
so,
I think. Like
when that happened, and became less connected with them.
Well, there was connections. There were students. You always had research assistants that were around. I mean, people like me who did that twice. I mean, it went from a employee to, and then became a student and got a master's, and then became a student and got a PhD, and so on. But there were other students. There were always students around. Some of them turned into astronauts, like Buzz Aldrin and I think Ed Mitchell and some others that were in the aero department at one
Dave
time.
Scott, was another one? Dave Scott?
I think so.
Yep.
These turned out to be students of Dick Batten. I mean, they all wanted to know something about guidance and control, and I think probably students of Wally Vandervelde as well. So there was a connection into it. Although I don't think that any of the people other than these students that I mentioned, I don't think that the employees thought of themselves as in any way as academics of any kind. I mean, they were working engineers in a laboratory associated with MIT, and there was some vague, let's say, organizational connection up above that certain MIT policies would flow down, whether it was retirement benefits or health benefits and other things of that nature, library cards and
Going to the faculty club.
going to the faculty club, things of that nature that you had. One big difference in the laboratory that, as opposed to some other laboratories like, I'm not sure about the radiation lab, but I know with respect to Lincoln Lab, Lincoln at that time was a line item laboratory in the Air Force. So they got their, the Air Force had a budget, and they said there's a budget for Lincoln Laboratories, and they did all their work under this budget item. And the instrumentation laboratory didn't have any budget angel in that sense, and they had to scrounge around and do their own marketing and find work and so on. And of course, Draper got this huge sole source contract to do Apollo, which was magnificent. But basically, the lab was not a kept lab. They had to get out there in the world and find that business, and that was a big distinction between this laboratory and some of the other MIT labs. I think the thing that Dan is referring to is that during the Vietnam War, there were tremendous student gatherings on campus here and all kinds of protests. And I think I had just left the lab, and I can't remember what the essence of what they were protesting at the lab. I think it was ballistic missile work.
Defense contract.
Yeah, just military and defense contract. They had no place in
At the
academia.
lab, you know. So you had
Besides,
the instrumentation laboratories. You had this whole section was Apollo, you might say, but there were other sections of the lab that were doing inertial guidance work for ballistic missiles and so on. And we heard stories of them having, barriers across the doors and bolts and this and that, and pressure on to divest the laboratory from the school, and eventually some accommodation was made with respect to the organizational structure.
All of us were in one building right around the corner here on Cambridge Parkway. We weren't over in Maine MIT. We were down towards Lotus. Lotus wasn't there then, a bunch of warehouses.
the building's gone now, right?
Yeah.
Yeah.
The building was gone.
Right next to the hotel, what's that hotel?
Sonesta.
It's like a
Sonesta.
Well,
layer
that was
cake.
a couple
Yeah, we
buildings
weren't
further
next
Well,
down.
that's
Yeah, it was
Charter
further
house.
down.
relative, right?
Charter House it was.
Right.
Oh,
Charter House, right.
was that what it was called? Oh, my
Before it
God,
was
I
a
forget.
Of course, Apollo didn't start in there. We sort of gathered into that building. We started in other places. The lab had, I don't know, that was W6, right? No, that was
W7.
7.
W5, I remember.
W6 was way down Vassar Street,
Yeah.
and then there was 1, 2, 3, 4, and 5, and so you had a garage, and you had an old shoe polish building, and so on. And Apollo began in these other buildings with various groups, a few people here and a few people there, and so on. And I can't remember the exact date when everybody was.
I don't know,
gathered.
we had the big computers down there in the first floor, and Dick Batten in the corner, and all of
Yeah,
us.
but I know Dick, when I went to work for Dick, he was in W1, near that elevator shaft that was in W1, and so,
On that fourth floor.
yeah, so it must have been,
With the 651?
About 62, we
yeah, it
were
must have
down
been
there.
like 1962 or so that everybody was gathered and brought into this one building. And you had things on the roof too, didn't you have a sextant and something on the roof of this building that they did star sightings?
Actually, when we all moved to the second floors, when you had the project organization and all of that, we took over all that second floor.
But I thought that that either Nevins or John Dolan or somebody had optical equipment.
Seemed to me that was down in 6, 224 Olin Street.
A lot of it was, but they had the thing on the
It was
roof
over-
that you can look at they had that thing you sat in up there, Doc Draper's toy.
Yeah. Yeah.
Anyway, there was quite a time in there, starting in the early 60s, and escalated as you got closer and closer to each flight. And I mean, Alex did the first one, 201. I don't remember the
202.
sequences after. The first few were all unmanned, and I don't even remember the
Yeah,
first
201 was
unmanned.
unguided. I think 202 was the first HEC guided flight.
202, I mean,
Yeah.
right. 201 was just open-ended.
Just let me ask you the last question probably. But did you have any international contacts? Did you go abroad to Europe, whatever? Do you have any contacts with foreign engineers? Was anybody interested from abroad in what you were doing?
I'm sure there was great interest, but I can't recall. I mean, it wasn't like Space Lab, where I did some work on Space Lab, where you had a real international group that you were.
Nobody in the world was doing much yet, and so it was all pretty early. There were individuals interested, but there wasn't any institutional interest that I remember.
There was huge
We
popular
presented-
interest.
Right.
We presented a paper in Paris at a conference on a theory that had come out of the Apollo project. It was part of our organization sent us there. So in that way, but it wasn't really what we did in Apollo, it was what came as a result of it.
Was any interest?
Very interested. I just can't remember, my mind.
That was about the
remember the name.
mid-'70s though, right?
Early 70s.
Early
yeah.
70s.
In other words, but it was still part of the Apollo group. The colloquium, programmation colloquium or something in Paris, mostly academics. But yeah, there was a lot of interest, but it was mostly academics, not application types.
No, during Apollo, most of our trips were to Houston, or for those of us that dealt with Rockwell, out to Rockwell, or it was all the business.
But some of us
Meetings.
were very shocked I was shocked when I first made a trip to North America, and we had, I don't know, you have the Cambridge scene here, everybody has his own office and everything's sort of quiet, and you look out the window, you might see the river and so
watch
on.
the planes take off.
Yeah, watch the planes take off.
From my
and so
office,
on.
that was my favorite
And
thing.
then you made these business trips out to Rockwell, to North America.
North American.
What you were faced with was this 3-block long open hangar, with God knows how many people in that
Yeah.
hangar, and telephones ringing and
fact,
noise.
The
and
fog, edge of the building was lost in the smoke.
Right,
and the haze
and
from
so on.
people
I
still
mean, the
smoking.
contrast, you wondered, how anybody got any work done. I mean, the contrast between what we used to think of as the aerospace industry and the norm of how people worked in this aerospace industry versus the norm of what we were doing at MIT was like night and day. I mean, it was just a different world.
Right. They were metal benders, and they wanted to build 10,000 more airplanes if we told them how. I mean,
Our offices look like graduate students' offices
Right.
at MIT. And you walk in there, I came from the meteorology department, and I felt like it was part of the same environment. It was not like a big corporation outside of MIT.
It was interesting in the early years to me to find that MIT people, we were never instrumentation lab people, we were always MIT people for a reason. Although we had this local environment of our own, when we went out to North America, we found that we were the communication means between parts of North American that we interfaced with that didn't talk to each other. And often we were the ones that told them things that their own management perhaps should have told them, but they were really glad to know, and we served a very useful, if inadvertent, function that way.
It's interesting that you say that, because the glue that Alex was talking about, when we put together the different powered flight and navigation and everything, we found that we were a communication vehicle, that the entire mission software for the different groups that were being interfaced as well. And that's how we learned about we didn't really know what was inside the black, or at least I was less familiar than you, inside the black boxes, but we really knew how they all tied together.
One more thing you probably should say about this, working at the lab, which was MIT, we were in a very privileged position. We got to see and talk to not only all astronauts, everybody at the NASA all over the place. I mean, Wernher von Braun would come and visit, and I remember giving him lectures on what we're doing and so forth. All those people we got to talk to as a small sort of elite organization. And when the flights were going off, the Apollo flights, we were tied in very closely on those headsets and boxes. I can remember one flight, I don't remember what, and who I was talking with in Houston, might have been Jack Garman. I said, it was a problem we had, and I said, I think we need an erasable dump, will you get one? Within 30 seconds on the main commander, Capcom, whatever, to the astronauts, MIT wants a dump, will you do it? Something or other. And it was always MIT wants this and that. And so I felt anything we did was going to get there and back very quickly. That might have been the time we were worried about the erasable being messed up. But
I also thought some people attributed sort of a pedestal standing to us that maybe I don't think we really deserve. But
Oh, yeah.
there's one thing that happened though that happened that I so vividly recall. It was near the end of there was a landing on the moon, and it was successful, and I mean the program, it either was it was just after that landing, or it could have been just before, but we used to go to these dinners at Lockovers, and I don't know how many where I went to, maybe 4 or something. And Draper was very expansive about this, and he'd want to get all those people there, and he'd always have some astronauts in there because that was kind of fun. And so I remember this dinner, and I was sitting next to Frank Borman, and we were eating dinner. And Frank Borman, somewhere in the conversation, he felt that the people at MIT, we were all sort of geniuses, and we were all, just these, I mean, almost like everybody was a guru and everybody was a genius. And then he said to me something like, you guys at MIT, you ought to get out of this program now. He said, this program is nothing but, it's going to be just grinding it out. He said, there's not going to be anything more of interest. There's nothing more that you guys can do. You ought to go off and do something bigger and more interesting than Apollo. And I thought that was interesting.
So we followed, so we followed Frank de Boer into Eastern Airlines.
That's exactly right. All right.
Yeah, we did have a good position, but also there were so many of the astronauts that had previous connections at MIT that we weren't poked fun at too much. We had some inside tracks.
I might tell you, just as a closing comment from me, is that Dick Batten has asked me last year to be a guest lecturer at one of his sessions. He runs a freshman seminar on Apollo, and he has these kids, and kids come in, and last year he had Harrison Schmitt, is that his name? The astronaut, and he had a number of other people, and I was there. He's trying to get Don Iles to come in, and it's really sort of remarkable. I only did it once, and so what you do is you're talking to these kids who are about 18 years old, and they really know almost nothing, zero. I mean, whatever they know from television and a cartoon, and maybe they read something or other. They know nothing. But it is interesting, the level of interest that they have in the program, and usually a certain percentage of them, like 4 out of 8 or 5 out of 10, they all want to be astronauts, and that's one of the things that drives them. Because you wonder why this person, as a freshman, takes this freshman seminar with Dick Batten on Apollo from 30 years ago. But it is interesting. Of course, Dick loves it, and I did bring in some artifacts. This is a program listing. This is this is that, and most of it is just getting up to a blackboard and drawing a few stick figures and telling them a little bit about how we got to the moon and something about the computer. And each person has something else to say. Of course, I'm sure that Harrison Schmitt gave them the whole astronaut viewpoint. It really, it is remarkable for these kids to have this connection through Dick Batten to this world, because it's something that very few people, very few high school students or very few freshmen in college could have an opening to, and to have these individuals appear in front of them. And Dick just, he just loves it.
Yes, it's something I felt. I know, coming from Europe, I've got friends and relatives there. The incredible intensity of that interest in Apollo, what happened. I often feel like, since I was in it, I haven't done my bit in satisfying some of their yearning for information and contact with this glamorous world. And that's just sort of a popular reaction. It has nothing to do with military, academia, or business or anything. The man in the street views the American Apollo program as just an incredible achievement.
If it ever really happened, maybe it would.
Indeed. This is from people who weren't even alive then, still there.
Yeah, we hope that the websites that we are working on would, one of its functions would be to provide a window into the history of that program for students, general audience who might be interested in that, so that they provide kind of both the basis in documents, but also that human subjective perspective on these events. So I wish to thank you all very much. It's been very, very
Your
interesting.
job is going to be a severe one in terms of getting young people now interested in things that, by comparison with today's technology, are so ancient and so primitive. Why would anybody want to look back at stuff, a machine that had a 3-bit opcode and a 12-bit address? I just bought the Microsoft Flight Simulator 2000, and it says you need to have 635 megabytes of disk space available. Good heavens!
Wait till you see
this
the operating system that comes out this fall.
If this is what the kids are dealing with, why would they care about a 36K word machine? And the problems that went with it that are just so completely removed from today's problems.
But I think this
Sort
could
of.
be a lesson.
It can be knitted into today, but that's a
I would
challenge.
like to make a comment about your, along with your comment, is I think that in looking around at software problems today, that they still have the same problems that they had yesterday. And I think many of the things that we learned and that evolved, lessons learned, could still be learned today. I mean,
Yeah,
the
I
hardware is
agree with
different,
that.
but I think software, in fact, is worse in many ways now. It's done in a more primitive way now than it was back then.
Because the resources are limitless, people just don't
Yeah.
try.
So I think we could go back and learn a lot, and a lot
Absolutely.
from what has evolved from that. So if we can't, then some of us are in trouble.
Right. So, I mean, look at history not as just progression of machines getting bigger and better,
Yeah.
but also it's evolution of human skill.
Of how you think,
Right. Right.
and model, and
Right.
design.
Right.
Exactly.
So, and some of those skills in the 60s might have been something very valuable that is not really in use now.
And sometimes we go back to the very foundations, the very core, and learn from what we might have thrown away.
The other thing is that people are, even though they can hold a handheld GPS in their hand, they're still interested in how people did things with a sextant and a watch, or not even a watch,
Or a disky,
or a disky.
which I sometimes call it by mistake.
Yeah, maybe we should have a simulator of a disky on a website so you can
Yeah.
actually press.
Yeah.
Press the
Oh,
three buttons.
That would be
definitely.
great.
I think so.
Yes, that would be great.
Then you can call up all the programs and get Jim's simulator going again.
P40,
Right. See how it
That's
crashes.
what we
Right.
can use.
yeah, priority alarms.
You can have your verbs and nouns.
Yeah.
All right, thank you very much,
Okay.
and
Thanks.
we'll be all in touch. As soon as we have a transcript, I will send to all of you for corrections and, adding details and all that.
I'd appreciate a copy of the transcript from the prior meeting so I can know
All
what
right,
people said
sure,
before.
sure.
Yeah,
Well, that
we-
hasn't been distributed
None of
yet,
us
has
have
it?
it yet.
No, but you know what was said
Well, if you
Now I
can
know
see your
what
mo-
Bill.